Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 4.3, day 1, entitled Logarithmic Functions. And today we're going to talk about the first two objectives. We're going to review logarithmic functions and then how to graph them. Now, in the previous sections, we've been talking about exponential functions. So this figure shows a graph of an exponential function. And remember that an exponential function is a one-to-one function. That means it'll pass the horizontal line test. So they have a couple horizontal lines drawn in here. And remember, to pass the horizontal line test, that horizontal line can only touch the graph of the function one time. And when a function is one-to-one and it passes the horizontal line test, that also means that it has an inverse. And the inverse of an exponential function is a logarithmic function. So that's why we're going to be talking about logarithms and logarithmic functions in this chapter. Now, the chart here does a good job of explaining how an exponential function is the inverse of a logarithmic function, and vice versa. And the way that we get that is if you take the original function that they had, the original exponential function, a to the y equals x. And if you're trying to solve that for y, to get any variable out of an exponent, you have to take the log of both sides of the equation, because logs and exponents undo each other. Now, ideally, you're going to take a log of the same base as the base on this power. So a is your base, so we would want log base a. Now what that does is it takes your y, your exponent, and it drops it down in front. Now the other property that we're going to apply here is that when you take a log of base whatever, of log a in this case, then you take that log of that same number or term as the base. So if you're taking log base a of a, then they will cancel. So you get y equals log base a of x, which is what they have over here. Now the way they've written it is a little bit more streamlined, I think. Usually you see logarithmic functions where the log comes first and then it's set equal to y. And that's good because the next thing we're going to be talking about is how to rewrite a logarithmic function as an exponential function so that it will help you to solve for any missing piece. And how we're going to do that is we're going to do what I like to call the circle method. It's not really a complete circle, but if you look at the equation, the logarithmic equation, and then if you look at the exponential equation, you can see that to convert a logarithmic equation into an exponential one, they start with the base, and then they raise it to the power of y, so we have a to the y, and then they set it all equal to x. So when you're looking at your logarithm, you're kind of drawing this little loop or this little spiral or this little circle when you are rewriting your logarithm as an exponential equation. So that's what we're going to practice on this next slide here. Now this says example 1, but really all we're going to do is we're just going to look at the chart and see how they go from a logarithm to an exponential equation. So for this first one, if we take log base 10 of 100,000 equals 5, the way you would rewrite it is you would take 10 to the 5th power equals 100,000. And 10 to the 5th is 100,000. For the next one, you would take 2 to the 3rd and set it equal to 8. And 2 to the 3rd is 8. Then you would have 2 to the negative 3rd, which is 1 over 8. Remember, if you have a negative value in your exponent, that means that you take 2 to the third in this case, and then you move it to the denominator. So we get 1 over 8. Or you have 5 to the r equals s. And if we knew the values of those variables, we could simplify that further. So we're applying that circle strategy here. You would take the 5 to the r power and then set it equal to the s. So we're going to use that skill here in example 2. Now, if it says to evaluate these expressions, we need to set them equal to something. That's what we're going to be solving for if we're evaluating them. And if you're going to use the little circle method, you need it set equal to something. You need an equation. Now, you can just type this expression into your calculator. Some of the TI-84s will even let you change the log bases and then type in a number. So it'll evaluate it for you, but I want you to practice this using the little circle method so you understand the concept behind the logarithms and how they're connected to the exponential equations. So to solve this, I would take 10 to the x power equals 1,000. And then you just basically have to say, okay, well, 10 to what power is 1,000? X is 3. So you don't need a calculator at all to do that for you. For part B, you'd have 2 to the x equals 32. And then you'd have to say, okay, 2 to what power is 32? Well, that would be to the 5th. And then for part C, you want to rewrite it. So you have 10 to the x equals 0.1. Now that decimal is a little challenging, I think. So I'm going to rewrite it as 1/10. 0.1 is the same as 1/10. And now it's easier to visualize that x is going to have to be a negative 1. Because 10 to the first power is 10, but then to get it into the denominator, my exponent would have to be negative. And then for part D, I will have 16 to the x equals 4. Now this one's a little bit more challenging. This one makes you think. There's a relationship between 16 and 4. If you take 4 and you square it, you get 16. Or if you take the square root of 16, you get 4. So the square root of 16 is 4, but we could also write that as 16 to the 1/2 power. So that tells me that x has to be 1/2. Now there are other ways to solve these problems. How you learned in Algebra 2 was that the bases had to be the same. So the 16 and the 4, you need those bases to be the same. So 4 squared is 16, and that's 4 to the first. And then when you have a power to a power, you multiply. And then once the bases are the same, you can cancel them out and just set the exponents equal to each other. And then if you finish solving that, you'll get x equals 1/2. So you can still do that. You can still think through these problems algebraically, but hopefully they're straightforward enough that you can use mental math on them as well. Now there's a couple properties on this page, a couple little tips that will help you solve logarithmic equations a little bit faster. And the first 2 tips are listed right here. When you have a log with a base and a power with a base that are the same, the log and that base cancel, and you just get the exponent to drop down as your answer. Same thing here. If the log and its base, and then the base on the exponent, or the base and the power are the same, then those cancel. And again, that x just drops down as your answer. So look for that shortcut, if at all possible. And then there are some other properties listed here. Number 1 and number 2 are different. 3 and 4 is what's listed above. But number one, if we use the circle method, they would have a to the 0 power equals 1. So just remember that. Anything to a power of 0 is 1. And for number two here, we would have a to the first power equals a. Okay, so remember that anything to a power of 1 is itself. So those properties are still going to apply when we're dealing with exponents and logarithms. So for example 3, there are a couple of these that you could cancel. And if you look at them, I'm going to go a little bit out of order, because if you look at them, hopefully you notice that part C and part D are problems where the base on the power and the base of the logarithm are the same. Even in part B, it's the same. So for part D here, that 5 and the log base 5 are going to cancel, and you just get 12 for your answer. Same thing for part C. That log base 5 and the 5, they're going to cancel, and you just get 8. Now you could work through that one where you rewrite it with the little circle method. So you could have log base 5 of 5 to the 8 equals x. You'd have to set it equal to something, and then do 5 to the x equals that expression, which is 5 to the 8th. And now your bases are the same, so they'll cancel, so x is 8. Okay. And you could even, you could do that for part B. You could set it equal to x if you wanted to, but you might recognize that this is 5 to the first power, and the base on that power and the base in the logarithm are still the same. So even when those cancel, you get 1. Again, if you didn't recognize that, you would just set it equal to x. Log base 5 of 5 is x. And then if you did the circle method, you'd have 5 to the x equals 5. So 5 to what power equals 5? Well, that has to be 1. And then for part A, you're pretty much forced to set it equal to something, because the log and the base of 1, they don't cancel. So you would have 5 to the x equals 1 if you did your little circle method. And the only number that would satisfy this expression would be 0, because 5 to the power of 0 would be 1. Anything to a power of 0 is 1. So you'll see some of these in your homework as well, where they'll want you to use these properties to help you simplify logarithmic expressions. Now when we're graphing logarithmic functions, you need to remember that there are a couple characteristics. If you have a function that's one-to-one and a function that is the inverse of it, then remember that the domain and the ranges are going to switch. So the domain of the first function will be the range of the second, and the range of the first function will be the domain of the second. And it doesn't really matter what the domain and range are. They could be all real numbers, they could be all real positives. Whatever the domain and range are, they're going to switch from the original one-to-one and then to the inverse. And if we graph an exponential function and its inverse, here's the logarithmic function. If we graph them, they have a characteristic where they reflect around the line y equals x. And again, that's a really important equation in math. A lot of things reflect about that line. And hopefully you also notice that the exponential function is growing rapidly, but the logarithmic function is growing slowly. And also the exponential function is going to have a horizontal asymptote of y equals 0. And the logarithmic function is going to have a vertical asymptote of x equals 0. So those are some other characteristics of exponential functions and then logarithmic functions when you graph them. Okay. Now, I have a little tip for you for when you're actually graphing exponential functions. This one we have the function of f of x equals log base 2 of x. Think of this as y equals log base 2 of x. And then even rewrite it because I don't know my log base 2 tables very well. Usually we pick values for x and we put them into the function to get a specific y value out. That's really challenging here. So we're going to switch the process around. So I'm going to take 2 to the y and set it equal to x. Now normally when we make a function table, we pick values for x and then we solve for y. But that's challenging here. It's much easier to pick values for y and figure out what my x would be. So I'm going to do that. So this is a little bit opposite of what you've been trained to do so far in your mathematical careers. But I'm going to start with my positive values. And if I put 4 in for y, I'd have 2 to the 4th. So that would be 16. And if I put 3 in, I would have 2 to the 3rd. So that would be 8. 2 to the 4th would be 4. 2 to the 1st is 2. 2 to the 0 is 1. And then we'll have our inverses here. 1/2, 1/4, 1/8, and 1/16. And again, I'm getting this because I'm doing 2 to the negative 4, or 2 to the negative 3, and so on. So now if I go to graph this function, I'll put in my axes here. And when I graph, I'm going to start at 1/16 negative 4, so that'll be really close to the y-axis. And I have 1/8 negative 3, again, still really close. 1/4 negative 2, 1/2 negative 1, and then 1, 0, and then 2, 1, 4, 2, and 8, 3. 16, 4 won't fit on my graph, but we have enough points that we can see that that is where my function would exist. Again, notice that this is going to increase slowly, and it's going to approach x equals 0, but it's never going to touch it. So that would be my vertical asymptote. The domain, the x values that I'm putting in are going to be all positive numbers. So x is greater than 0. And then my range would be all real numbers. I wrote my r's backwards there. Okay, so my range would be all real numbers. And notice that my x-intercept is going to be 1, 0. Now remember, for the exponential functions, when we graphed them, they all went through the point 0, 1. So now, since a logarithmic function is the inverse of that, they will all go through 1, 0. And that is what is pointed out in this slide, that all of the logarithmic functions will go through the ordered pair 1, 0. So we've seen several characteristics now of the logarithmic graphs. How logarithms and exponents are inverses of each other. They reflect about the line y equals x. They all go through 1, 0. They have vertical asymptotes as opposed to the exponential functions that have horizontal asymptotes. Okay, so there's a lot of those characteristics that we've been talking about with exponential functions that are just reversed now for logarithmic functions. Okay, now our last example then is to graph these two functions. And in example 4, we had log base 2 of x that we were graphing. So this is basically the same function, except they've just changed it slightly. They've added a negative in front of the whole function for g of x, and they put a negative in with the x for h of x. Now, just doing that one simple thing is going to change our graph just a little bit. Now, this is the property of transformations that I want you to remember. If I put a negative out in front of the whole function, that's going to change my y values, or in this case, my g of x values. So instead of having -4 to +4, I would start with 4, 3, 2, 1, 0 for my table of values. But my x values are going to remain the same as the other function that we had in example 4. So this is the same table of values, but that negative out front of the whole function just switches the signs on my y values. And then for the other function, if I put, that's an x, if I put a negative inside the little parentheses there with the x, that's going to change all of the x values in my table. So my y values, or in this case the h of x values, will be the same as that original table that I made. But now I'm going to change the signs on my x values. Oops, -1. So then if we were to graph those functions, the graphs are shown on the next slide here. So this is my original function that we graphed in example 4. And then if I graph my table of values that I listed on the previous slide, I will get this red function. So remember, this negative out front of the whole function changes the y values in my table of values, and then it flips the function upside down, basically. It rotates it around the x-axis. And if I put a negative inside the parentheses with the x, that affects the x values in my table of values, and it's going to flip the function around the y-axis. It's going to rotate it across the y-axis. Okay, so keep those properties of transformations in mind because they're still going to apply. Use them as shortcuts. You can still substitute, or I'm sorry, plug this equation into your graphing calculator and get a table of values. But the table of values that we need has to be kind of specific since we're working backwards. And these fractional values may not show up on your graphing calculator, like the 1/6, 1/8, 1/4, 1/2. So don't be dependent upon your graphing calculator when you're dealing with this set of homework problems. Try and do this on your own. You can use your calculator to double check your work, but don't depend on it to do the graphing or the evaluating. And make sure you show your work, even though there's not a whole lot of work to show. Make sure that you're drawing in the little arrows for that little circle method, or rewrite the equation and then write the answer. Make your table of values when you graph. And if you have any questions, step on in before school and see me.